very good evening to all of you. And first of all, let me thank to the organizer for inviting me and sharing my knowledge with mainly with the students and the faculty members on this particular topic of the stealth aircraft design. So I'll be I have a mic. Audible? Yeah. So we will be talking mostly onto the aircraft, basically the kind of the aircraft now the country is working. So even not only the aircraft, if you talk any of the airborne platform, what we are talking is this is the word which we are calling as the stealth is coming into the picture. Also the recent the operation which has happened, you will understand that how critical is this particular technology if you are building any of the new platform for the development of the country. So I will just try to highlight that what is the scenario across the globe and what is going on. I cannot show much on to the what we are doing, but we will be give a glimpse of the some of the open literature things, and which will give you idea that what are all the areas where the students can also contribute and what we are doing in the lab levels and where we stand today. So we will show something, start with some basic history and what is the purpose of the stealth, what exactly the stealth does when the aircraft we are talking about, and I'll show some of the in the Western country how the stealth aircraft development programs are happening. We'll show a very brief on the how the aircraft design cycles, how we design the aircraft, what all the process is involved, because that is very important to understand if you want to design any of the aircraft. So we'll briefly touch about the aircraft design cycles, and then we'll be showing that how we design a stealth aircraft. So and we'll show one MDO problem where we'll show that conventionally if you design an aircraft versus the stealth aircraft if you design, what is the differences, what all the challenges are there, and some of the automations in the AIML. This is the areas where a lot of activities in the R&D domains are happening specifically to the research area. So I've kept few of the problems here specific to the students, which will help them to understand the problem where AIML also in this domain, how to utilize that, and some of the futures way forward, that what is next we should do, where we stand today and what is the next we have to go ahead, that will be showing along with the concluding remark. So basically this word has come in public discussion in around 1980 when the US Air Force has launched a program which is now called as a F-22 Raptor aircraft. This word is known to us, but around 1982 it has become so sensitive. It is the word wherever we are writing stealth in any document, it comes in the category as classified. So it is not accessible to the general public, any of such document. So it has become in 1982 roughly, it is very sensitive, this domain of the stealth, because there was a program, few programs by the US Air Force was launched at that time. So stealth, it's not a technology basically, it's it's a quality of a weapon system. Like if you say that I have a missile which can go 100 kilometer, or what is the speed of the vehicle, similarly it is a stealth is some numbers are there which define the weapon system. And basically in the US Air Force, if you see all the black programs, it is called as a black program. So when you are saying it's a black program, means it is a stealth driven. In many of the times, maybe if you see for example F-117 aircraft and all those things, so it is not designed for the aerodynamics, it is designed for the stealth, and later on it is seen then how to fly this aircraft. So sometimes the primary factor for the design of the aircraft will become the stealth, not the actual aerodynamics of the particular bird. So it is a very important aspect to look into. So what it does basically, so it is basically, when you are saying it's a stealth, it improves the ability of a weapon system to carry out the mission by making it more difficult to detect. So I kept few images here. It's for example, just for the better understanding. So if you have in all these three images, there are few objects are there. Here it can be seen, but here it is too tough to see that. So what we are saying that if you have any object and their signature is by the background noise. So if you see the background is similar to the particular object itself. So if your noise level is fall into the noise level of those particular background, I mean for your visual, because this is the visual signature. So my eyes, it's finding it difficult. It will take some time to detect that. So the same way the radar also does. So what you are trying to say when you are saying you are making an aircraft as a stealthy, we are making the signature low and trying to see that it's fall into the noise level of those radar systems, so that the radar will get confused or it will take longer time to detect this thing. So basically we are doing the intended to delay the detection so that we can finish our job and come back safely without damaging our aircrafts or the systems. So in general, in a layman language, if you'll see, if I have a non-stealthy aircraft, it can be seen by the enemy radar from a longer distance. When you are talking about a stealth, I can still go closer, so before getting the detected. So in this case, if you are non-stealth aircraft can be seen from the far against the radar, stealth aircraft still can go. So I have the benefit of this much distance. So that distance can be X number. So when I am saying the delay in detection, so but in actual case, if you want to have a true stealth aircraft, what we say, so basically when you are talking about a true stealth aircraft, its goal is to achieve the high level of the stealth basically. What does it mean? That the probability of that particular bird is that it will perform its mission without being detected at all. So your numbers are so low. So it's a truly stealthy when I am saying means it's a so low signature. It will do the job, radar will not be able to see, it will finish the job and come back safely. But the word, this is what you are calling is a probability. It's a probability. So it is not the realistic number. So it will vary, depends on the various parameters. So when we are talking about the stealth, it doesn't mean it's invisible. There is nothing, no aircraft is invisible. I can see, maybe my radar can see one aircraft which is non-stealthy, maybe 200 kilometers. The other aircraft may be seen at 100 kilometers. Some may go closer to 50. So it is basically up to what range you are going, that is what the level of the stealth we are building onto the aircraft. So finally, if the probability of the detection we are reducing, so basically there is a chance that the aircraft will survive and complete its mission. So the survivability will increase, the chances of completing the mission also will improve. So that is the basic fundamental of the stealth. So from the literature I have taken one test case here. So there is one operation of the 1972 Linebacker, where it is shown that around 70 aircraft has been used for doing that mission. Out of that, there was only few aircrafts which was carrying the offensive weapons. Rest of them was either the escort or the EW or the jammers and other thing. So to take out of 70, maybe the 10% of the aircraft to do missions, a lot of the inventory used to be required. So that time this thought process came, can we look into this EW problem seriously in a different way, by see that how we can reverse the problem by increasing the detectability. So that is what the signature has come, and the people are looking into that. Can we reduce the signature of the aircraft? Can we build a bird with a low signature so that the rest of the inventory can be removed? So now if any aircraft which has to fly and do the missions, so this will become hardly a 20% of this particular total number of the aircraft. These are some of the development in the western side. So this aircraft SR-71, you leave it. For example, F-117, this is one of the first early stealth aircraft which has flown, and later on it has happened so that this bird initially in the few flights it was doing its mission very nicely. Then later on it was observed that when it was going to the same route again and again, and these birds basically carry the weapons inside the belly. So if you are carrying anything outside, your signature is increasing. So we have to carry that anything inside the belly of the. So the belly is a kind of cavity. Once the cavity opens, any cavity is not good for the stealth. So any cavity creates a lot of signature. So whenever it is in off condition, it's good. But when dropping a weapon, when the bay used to open, the signature is to increase. This bird got detected and twice it got shot down. Then later on they improve onto the design of that, and then this is the one which came is what I was talking in around 80s, the F-22 Raptor, and now they have the F-35 Joint Strike Fighter. And similarly there are few bombers are also there. So these are all comes under the manned aircraft category, in which a pilot sits and fly the aircraft. What we do is basically it's unmanned. So there is no pilot sitting onto the aircraft. So it will be completely unmanned, so autonomous. So from taking off to the landing, there will be no pilot. Sometimes it will be external pilot, sometimes it will be totally a pilotless aircraft. So it will be of the similar size and shape. So it is not a small drone. It will be of the similar to what we see onto the many of the fighter aircraft. Maybe in the Aero India people must have seen. So it is of that class of the aircraft on which our lab is working. So here I have shown just some of the aircrafts which is from again from the open sources. Again these aircrafts are basically for the strike missions. It carries the weapons, bombs. It is shown in some of the cases here. So I have shown both the manned and the unmanned aircraft doing the similar kind of the job. Now a little bit onto the design side. So what happened when you are talking about the stealth? There is always a requirement comes from the users. So user says that I want a aircraft to be look like this. It has to have the range of this. It can carry this much weapon. It should do what. So there are performance and other things will come, like for example in terms of the mission requirement, aerodynamics, weight, they will say it should not be more than 25 weight ton class, dimension should not do this much, it should be restricted to this. So this is all the conventionally when we design an aircraft. So it is up to the 4.5 generation aircraft. This was the conventional way to look into the definition of the aircraft design requirement which used to come from the user. Now when we are talking about the stealth, it is called as the 5th generation or more than higher than the 5th generation. So when you are talking about the stealth, this is the last number I have written. It's an electromagnetic requirement. There is a word called as a RCS, radar cross section. So that also is coming as a input, as a requirement. So user is saying you design an aircraft with rest of the parameter plus you give me the RCS of some numbers so that my signature of the bird is this much. So that is called as a stealthy bird. So there is an additional number is coming as a definition itself. So now what is the impact of this, which I will show in the subsequent slide. So just for the student to understand, then once the definition comes, we try to see the feasibility. In the feasibility, in the basic level, we will see some different class of the configurations in a very crude way and try to see with using either the simple formula or the thumb rule or the some not going into the much details and try to evaluate that whether this will be the configurations. Out of 100 of configurations, by seeing those things, and we'll try to converge into some 8 to 10 configuration in the initial feasibility. Then we'll take it into the which is called as a preliminary design, where we'll look into the more detail. For example, I have shown one case. So I have a wing. So I will see that what is should be the sweep of the wing, the leading edges, angles, the intake, the air duct, where the air it is carrying to the intake, where to mount on the top or the side or the bottom or the Y shape or the straight. So like the detailing things keep on happening and goes up to the detailed design. So once we are saying the detailed design completed, means the aircraft is ready on a paper. So design is ready, but we are not started fabricating that aircraft. So that is the way, so it is reached up to here. So this is all happens only onto the computers. So it's all simulated and the design activity. But parallelly many things happens for the development of the technology to prove that the definition to reach up to in this level. So after that the fabrication starts for the any of the aircraft. So now this is the very big the catchy area. Now there are multiple disciplinary. When you are talking about a aircraft, it's a system. So for example, what I am written here, so it's taken from the internet again. So what is you are seeing in the black is basically is the conventional aircraft what we design. For example, now if you see that what I have written here, conventionally the aircraft initially used to design for the better aerodynamics. So it used to do the better performance. Now when you are talking about a stealth aircraft, we want to have the signature also. So it is becoming a coupled problem between the aerodynamics plus the electromagnetic. So now sometimes it will be reverse also. The electromagnetic will be dominating the external shape of the aircraft because the requirement is such that. So there is no more a single domain. So it is becoming more and more complicated and the multidisciplinary problem. Similarly, in the conventionally in the aircraft, if you see, I will show a few of the slides. So we used to position the antenna and the sensors all across the aircraft mounted outside. Because the antenna has to be radiate, it has to give better performance, coverage and other things. But when you are talking about the stealth aircraft, these are all not good for our aircraft. So the technology called as the conformal antenna, shared aperture antenna, it has to be mounted with the aircraft surface only. So there is again, so what I am trying to show here, any discipline you talk about on the aircraft, the stealth has an impact onto that. Similarly, for the propulsion, conventionally we need to have, if you see the Sukhoi aircraft or any of the aircraft, you can see if you stand in front of the aircraft, you can see the engines very clearly. But those kind of the straight engines has again a problem for the signature. So we need to have some serpentine air intakes, which you will see in the internet, a lot of things. So intakes are bent to hide the engines from to reduce the signature. Once you are bending it, your thrust performance may go down. It may have impact on the aerodynamics performance. So it's becoming again a multidisciplinary for the intake design also. Similar way, the weapons. So weapons, conventionally any fighters, if you see in the pictures, it will be all mounted either into the wing or onto the belly of the fuselage. But these weapons, if you are mounting outside, you need to have a pylon systems on which you are mounting the weapon. So these are all again creating more and more problem for the signature. So we want an aircraft which should look like a clean aircraft. So now only the aircraft has a no purpose. We have to carry the weapon. So how to take it? So normally what we do, in the belly of the aircraft, there will be a bay inside which the weapon will be carried. So there will be no weapons outside in the stealth aircraft. So we need to design an internal weapon bay. Again, it is a unsteady aerodynamic problem because the cavity problems, releasing a weapon from the cavity and the synchronizing the opening of the door and the plus the reducing the signature. So it is again a couple problem. Similarly for the manufacturing, conventionally conventional manufacturing may be easier for doing the conventional aircraft, but this kind of the aircraft require very tight tolerances so that to avoid to reduce, even though I design the aircraft on a paper, it looks good, but if I cannot fabricate with that kind of the tolerances, again my numbers will not be meeting. So in totality, if you see whatever domains on the aircraft we will talk, it has impact on the signature, or it has to be designed in consultation or in collaboration with the electromagnetic team. So that is why it is called as a multidisciplinary problem. So it cannot be done in a standalone mode. So one problem I have shown here. So when we design a conventional aircraft, so we are looking for the drag. Drag of the aircraft should be low. People will say it should have a light structure and I should have a internal space enough so I can carry more fuel and more the sensors and the other LRUs onto the particular aircraft. So the requirement comes like this. And so our objective problem will become that I have to minimize the aerodynamic drag, I have to reduce the structural weight with some design variable, and the constraint is given to this. It is a multidisciplinary, but I will show that when we do an aerodynamic problem, so it has an impact only to the aerodynamic shape. So it does not lead to the more impact onto the other domains. So there will be then aerodynamic shaping will be done. So it has only the aerodynamic optimization will be done, and once the load is generated from the aerodynamic will be given to the structure guys, and the structure will be designed for that load and it goes in that cycle. So it has a individual disciplinary wise the penalty or to the impact. But when you are talking about in the same problem, I am adding the electromagnetic into the loop. Now initially I had a drag issues and the weight. Now I am talking about the additional terms as a low signature. So I want to have the aircraft to be low signature, and now the internal space which you are initially asking, now we are asking more space because I have to carry the weapon also inside. So in my optimization problem, also in the constraint, the RCS has come into the picture. Now the internal volume for holding both the fuel and the weapon. And the discipline now, if you see, initially it was aerodynamic and the structure, now the stealth electromagnetic has come, and in this lot of materials studies has to be done. So material science is becoming one of the key aspect into looking into this particular aircraft. So in totality, now when you go to the optimization problem completely, so now the aerodynamics cannot be done standalone because the stealth has come into the picture. Now, so it will become a coupled problem. Similarly, the structure. Now the conventional material we cannot use because we have to use some kind of the absorbing material. So again the design which is done for the structure also. So what we are trying to say that stealth has a larger impact onto the other discipline. So it cannot be done in the isolation. So this is becoming a multifold MDO problems when we are talking about the stealth, including into the aircraft problem. So we said the signature to be reduced. So normally that word is called as a radar cross section. So in a layman terms, you have one transmitter, so there is energy is going and you have an aircraft. We want that energy, minimum energy to be come back to your receiver or the antenna where you are mounting. So what we do, we define, I will show in the subsequent slide. So we define some kind of the sector of the aircraft. Okay, we will show in the next slide. So the end goal for the designer is that we should understand the where is our transmitter or the receivers are there, from the where energy is going and where we don't want the reflected energy to go back. So as per that, the shape of the aircraft will be defined so that it is not reflecting to the area where you want, it is going somewhere else. So this is the basic principle which we use for the defining the RCS. And this I will not go to that formula. So just to understand that, if a normalized way, if I have a RCS of 1 and it can detect from the 100 kilometer, so if you are reducing a one order of the signature, for example, there is a benefit of around 44 kilometer range. So but if you see afterwards, the another one order of reduction, there is not much significant. So reducing a signature after a certain limit, it will becoming too complicated, because it will be having impact onto the lot of other parameters like the weight penalties, the configurations and other things. So we have to see balance between the aerodynamics and the structure, how much we can come down and what benefit we are getting. So I was telling just now that we want to have that energy to go somewhere else. So we define basically the threat sector. So for example, there is an aircraft here. So we will see that what is the purpose of this aircraft. This has to penetrate to the enemy territory, release the weapon and come back. So basically on the frontal part of the aircraft, that sector will become more critical. So we define that which sector is critical for particular designing of the aircraft. In some aircraft cases, it may become all the sector throughout the 360 degree may be a critical sector. So we define the threat, where is the threat sector, accordingly we will give the more priority on that region, that my numbers on that region should be lower compared to the other part of the aircraft. Then also we define the angular coverage. My aircraft may be flying at the ground level, it may be flying at the 15 kilometer of the altitude. So based on that, and you have the enemy radar sitting on the ground or the air to air, so based on that we will try to find out what is our angle coverage. So we will define both azimuth and the elevation coverages in terms of that. Then comes to the frequency, against which kind of the radar we have to design this bird. So there is a large number of the frequency bands are available, from UHF, VHF to the XKU band up to that. So it is very tough to design an aircraft across the band of the frequency. So we have to be careful that what is our target or the requirements for looking into this. And not only the radars, then it will be monostatic, whether your transmitter receiver are sitting at one place, or it is at the different place located, or the polarization of the radars. So there are multiple n number of parameters are there which has to be taken into the consideration when we are talking about the design of the aircraft. So okay, this is the kind of frequencies are there. So now here is the catch. Now you may ask that you may have a requirement, I want an aircraft, a stealth aircraft, which should work, for example, I am just taking a random number. Let me take for example the UHF, for 0.3 gigahertz to 18 gigahertz I want a stealthy bird. Now this is the requirement. So I will show in the next slide. So how the RCS varies. So if with respect to the wavelength, so when you are talking about the 10 in the electrical size, for example, if your aircraft is a 10 meter in dimension, and if it is in the 1 gigahertz, so it will coming into the 10 times of the wavelength. So 1 gigahertz frequency for 10 meter of the bird will fall into the optical region. So once we are into the optical region, it's much easier to shape the aircraft. But if it is going lower than that, it will be becoming too tough, because it will be resonating and your signature will be keep on fluctuating. Sometime it will be more, sometime it will be less. So now if I am saying that if I have to design a bird with a 0.3 gigahertz of the UHF, so I have to multiply that dimension, so it will become a very huge bird. So it will like a B-2 bomber kind of the thing. So it cannot become a fighter aircraft, it will become a bomber. So we have to understand the physics first, then only we can implement. So we cannot say that design a small bird which should work on those frequency also, which may not be physically possible. It can be done in other way, but in that case you have to treat the complete aircraft with a very heavy loading of the material, so weight will go exponentially very high. So these are all so size matters actually, so we have to be very careful on that. So the same problem I have shown here. There is an aircraft, assuming the length is around 13 meter. So at some frequency it will be onto the high frequency scattering, so we can shape it clearly. But if you go to the lower side, their signature will be higher, sometimes it will be lower, it will be keep on fluctuating. So we have to be careful on designing when what we are doing. So once we have the requirements, once we have the problem definitions, and we know that for which particular set of problem we have to define a aircraft. So this is a typical cycle what we do. So based on the previous experience on the available database in the market, we initially design a CAD model of the aircraft. Again, some open models have been shown here. So we used to have some CAD model. Normally we use CATIA in our industry. So once we generate the CAD model, then we'll convert into some kind of the grid. We do the meshing of that for the electromagnetic, and then that goes for the performance assessment in terms of the RCS. So we'll try to assess the performance, that how good or bad is that shape. If it meets the requirement which I showed in the previous slide, if it meets the requirement, we say it's a selected or the final configuration. If it is not meeting the requirement, then what we do, we try to assess that the hot spots and the region from where the scattering is coming, and where the energy has to go other direction but is still coming. So those regions, whatever these red spots you are seeing, we'll try to see that can we reduce that or can minimize this. So we'll do the diagnosis of that, and we'll try to optimize and refine. When we are talking about optimizing and refining, so it will not be single domain. I cannot do independently because I have to get it involved with the aerodynamics, I have to get it involved with the controls, structure, so various disciplines. So all will get and look into that what refinement has to be done, and then again model comes and it goes into the cycles, and until unless the final configuration is arrived. Once the final configuration arrived, because I showed in the preliminary design and the detailed designs in the previous slide, so once it is a final configuration arrived means, then we'll do some kind of the testing of that. So we'll make some scale bird or maybe 1:1 model for the electromagnetic performance testing, and take it to the labs where the measurement facilities are there, and try to evaluate that what we simulated and where we stand, and do the comparison. So to designing that particular bird, so one thing is the shaping, where we'll try to divert the energy. So different concepts are available for the shaping, and then we use lot of materials in terms of the structures, paints, and lot of metamaterials are also getting involved into this. And third things come into the manufacturing. So we have to be conventional manufacturing. I said it's not, I will show few slides, you will understand that how the manufacturing has been shifted for this class of the aircraft. And all the components, you talk about anything, whether the weapon systems, air intake, antenna, actuators, air data probes, or any of the control surface, everything has to be designed for the stealth. So it will not be a conventional things, which a few slides I will show. And then we have some thumb rules that will take into the consideration when we are designing. So what we say, suppose for a given number is given, let me take the number of this 20 dBSM. So I have to design an aircraft with a 20 dBSM. So what we do, one down, one order lower. So 10 dBSM will be the major subsystem. So we'll split the aircraft. For example, air intake will be 10, like 10, 10, 10. And the aircraft, if it is having a 5 sum component, then we'll go one down. So that is a basic thumb rule which we use for designing the basic subsystems, and then keep on integrating to design the complete aircraft. So in a non-conventionally designed aircraft, so normally the signature will look like this. So everywhere you will see the spike. So it's easy to any of the system to get it detected. When you are talking about stealth aircraft, so we are intentionally diverting the energy at some very focused direction based on our design requirement, and minimizing the signature at all the places. So that is the basic fundamental when we are doing the external shaping. We are diverting the energy in some focused direction to avoid the signature of the complete bird, and the rest of the areas it will be a very low signature. So this is the kind of the, once we do the design completion, then we'll take to some of the places of the labs where we have facility to do the measurements. Normally either we do some kind of the anechoic chambers are there, where we can do the scale down model and the measurement for the initial development of the programs. Once the program has reached to the very advanced stages, we sometimes make 1:1 of the aircraft. If someone has gone to the last year Aero India, their time 1:1 model of the AMCA was shown there. So those models can then go to the test facilities and can be placed either into the anechoic chamber or into the open range, or sometimes into the pylon kind of the system, where we will measure and see and check the performance that what we designed is matching or not, or if something mismatch is there, and to relook and correct the models. I said that in the previous slide, the manufacturing. Now if you see here, these particular slides where we have shown, conventionally in the aircraft or any of the part, if you see joining, there will be two straight lines. If some mechanical guys or the fabrication guys, two components, if you are joining, it will normally be a straight. But that straight edges are having a problem. So this particular bird, if you see, it's all are having some special kind of shapes, which is normally we call as a serration. So this is for the reducing the signature of those discontinuities into the skins. So the skins also need to be serrated. So this is again a complicated design. So we cannot have the conventional way of fabricating the components. So now if I have a serration, so suppose my part was ending here, now I have made a serration. So now my tool design, so tool is becoming longer, part is becoming longer. So where you are mounting this particular the skin, so your frame size is becoming longer, so it may have a weight penalty issue. So and also if you notice here, which is I highlighted some places, so those are all some of the antennas. So those are all conformal antennas. It's a conformal, but now if you see the shape of that, it is some kind of the diamond or the hexagon shape. So how to make a cutout of the antenna also is important. So it is not only the antenna design. Now antenna has to mount onto the aircraft, also has to be looked critically. So once we have those serrations, now if you notice, I have taken again from the internet few images. You can see nicely here a lot of chip off of the skin. So what they do, the serration is one way to reduce the signature, and then they will put some special coating of the material to further bring it down. So if you see, there are you can see clearly notice that there is a lot of the paints have come out. So these are the special paints basically. So paint has a problem. Even in the wall also, if you see, if you put it, it has a life. After some time it will come out. And because these paints are quite thicker in terms of whatever we use in microns, it is in mm. So it's such a huge load that it's always probability that this kind of paint will be chip off. So we have to look into the alternative scheme. So what we are designing now, which is called as a radar absorbing structure. So basically we are, when you are fabricating a composite, this material are getting infused into that so that it will be co-cured, I mean the cured itself into the, when we are making the structure. So it will be not a kind of paint. So it will be a structure which will take the load also, and it will work for the electromagnetic also. So that is one of the area where metamaterial based, FSS based radar absorbing structure, a lot of activities are happening. I will show a few of the things on that. Same thing, so conventionally the conventional doors and the patches you see, and then fastening mechanism. Yeah, so here I am shown that. Now what we have designed, that is for the next generation aircraft. There may be requirement that, okay, you did it for something, can you implement into the existing fleet itself? Doing that sometimes may become challenging, because that bird is not designed for that intended performance. So here I have taken few images of some of the aircrafts from the open literature where those serrations has been those serrations has been done, but you can see there is lot of chipping off and the discontinuities and other things. So putting the, so it is always better to, when you are doing a ab initio design, use this all the concept in the beginning of the program. Later on adding something may not be a fruitful thing. So it may be a more problematic in terms of the maintaining those particular birds. In terms of the sensors, again I showed previously also. So conventionally we will see if you have all those sensors projecting outside, but this kind of the bird, the stealth bird, nothing you can see. It's a completely flush screen. So skin will be completely flush. You will not be able to see anything out. And these features, whatever is there outside of any of the birds, which is non-stealthy aircraft, whatever we do, we will put extra material or some treatment, it cannot reach to that level. It will reduce slightly, but it can never be reached up to this level. There are few things, this is also one area where a lot of activity is actually required. Basically, if you see those glasses, colorful glasses, what it does basically, it's called as a optically transparent. So my eyes can still see, but for the radar it is a metal. So those colors are, it's like a reflecting. So we are designing the canopies and the wind screen, shaping it like that it is a metal, so that shape energy is diverting somewhere. But for my eyes it's optically transparent. But what you are seeing, so there are different classes of material like the gold coating, ITO, indium tin oxide, those coatings are available. which is been coated onto those kind of the structures or the glassy structure to make it more reflecting, so that, because otherwise that cockpit is a huge cavity. If it is not reflecting for the radar, it will be a cavity, it will throw a lot of signature. So this is another area where a lot of activities are happening on. Okay, so basically the what coating things I was saying that, so basically what it does, either it will be, that coating will be, see the green curve if you see on the left side, if you are not coated, it is 20% reflecting, but if it is coated one, it is almost 80% that the skin has become a reflecting, and rest is also becoming an absorber, so it is not transmitting, so we don't want any rays to be transmitted. Also these birds, there is another problem. Now when I said in the beginning also, when you are opening the weapon bay, it is again a cavity. So now there is a look into, to see this particular bird, we study that how we should fly these birds while opening the weapon bay and releasing a weapon. If you see in some particular cases how the weapons are getting released. So we have to also understand that what is the best way to release the weapons, so that still my bay is open, my signature is low. So it cannot be a conventional way of opening the bay and releasing the bay. So we have to see that what alpha beta condition and what maneuvering this has to be released. So that also is another area where lot of if someone is from the controls or guidance, is there a lot of path planning and how to do the weapon release and other things, is a lot of areas where a lot of activities can be done. Coming to the last part, where basically this particular domain is electromagnetic, is again computationally very highly costly. So we need a lot of high performing computers and other things. So we are taking up some of the activities like which we call as automation. So in this particular case, what we are saying that, so we have generated some libraries. Okay, now it can tell, so the orange curve what you are seeing is what my boundary. So that is the definition. So that can be varied. So I can put it some input, and then I can simulate any bird, and then I will say that where it is crossing that, I will say that your bird is not meeting the requirement or something. And also now I have a material libraries which I will show next. So that we can tell also that to reduce this further down, what I should do without simulating anything, because I have the libraries. I will just infuse those data. Those are realistic materials, it's not a dummy material, and it will try to tell me that which portion of the aircraft if I will use that. So it is reducing my the effort. So we have to do a lot of automation activities. This is one of the things. So here the other automation activities. So now for example, now there is a one aircraft, it's a commercial aircraft with a 4 engine. So now this 4 engine is showing some signature which is we have plotted here. Now if somebody will ask, okay, assume that this aircraft is only having 2 engine on the one side, what is my signature? So without doing any computational effort, because we have the library available with these automations, we can remove those engines and we can tell that how much will be the signature of, without doing any of the simulation. We can save a lot of time. So there is a lot of such activities has been done. For that in the backbone, lot of AI/ML codes have been written. So it is helping us to reduce. So we are generating a lot of libraries. So these are all one of the area where a lot of activities are happening on the automation. Now the computational electromagnetic using the machine learning. So conventionally what we do, for example, if I have to generate one kind of SAR image of this aircraft at one look angle, normally we run this many cases, around 5,000 cases. But now with the AI/ML, we can reduce this to roughly around 50 to 90%. So if I can train with the 20% of the data, 30% we have shown different. In the initial design activities, now if you see, with the 30% of the data only I can predict that this is a 4-engine aircraft. I need not to be looked into very particular that how does, because in the initial design phases what happens, the iterations happens very frequently. Indicative idea itself is good enough rather than looking into the final numbers. So if even though it's a 20% off, it's okay for me to design iteration. So machine learning AI/ML is doing a lot of support or help us to reduce the computational time. In this case around 50%. For example, next case if I will show, I am seeing this aircraft from the broad, from the side of the aircraft, with only 10% of the data I can generate the image. So almost 90% of my computational time has been reduced. So This is the area where a lot of activities are happening, but we cannot use it blindly. We should understand the physics, then use the machine learning things. Otherwise, it will be just running some model will never going to work. On the material side also, there is a lot of AI ML. Now here what we did, this is recent work. So conventionally what we do, we take some geometry in the metamaterials, which we called as a unit cell, and then do the parametric study and see how the reflection parameters or how the RCS performance is coming or the absorption of the material. Now we have trained a model in an inverse way. We said as a designer, I am not worried about what is my unit cell and what I want. I will say that I want a reflection or the absorption from this to this frequency, this much percentage. That I will feed as an input. It will automatically generate me a unit cell or the RAS design and give me the solution. So this is what we did it. So now we can blindly, not blindly, but we may not be required a more dedicated EM guys, or because these models are ready. So I can tell to the beginner also, you feed this data, he may not be knowing, but my purpose is solved because we have trained the model, generated the things, and we are utilizing. So what I am trying to say that in machine learning, a lot of activities are happening in this domain, whether you talk about the material or talk about the automations, in all the discipline, not only on the electromagnetic. Yeah. Yes. Yes. Transmission. Yes. So we want transmission, reflection to be avoided, and because you have a metal at the back, it will not transmit also, so it is has to absorb only. Okay. Yeah. Yes. It's not exactly, but more or less yes, because we have basic fundamentally. If you see, either it has to be so. It's okay. When you are talking a material, so material. So totally, if you see, when we do any measurement, so we will have a two-port measurement. So here we will be transmitting, and other port which will be taking a data. So the data which is passing through and receiving to the other, that is the transmitted. Some data which will be reflected back. So we have a reflection and the transmission. So remaining that, if you from the one, if you minus, it will be called as a absorption. That is a straightforward. But the material what we want, because in actual structure of the aircraft, if you see, we are keeping a metal behind of this material. So it will no transmission will happen. So either it will reflect or absorb. So we want reflection to be minimized, so maximum to be the absorption. So the material has to be designed so maximum energy has to be get absorbed. So but we should not blindly use the absorption also. So first what we do, the shaping of the aircraft. We shaped it, try to minimize the signature. On top of that, then we'll put a materials to further bring it down the numbers. Otherwise, if you directly put a material without doing a shaping, it will be a suboptimum configuration. It will not be optimized. Yes, that is the first choice. Later on you put a materials, because material has a weight impact also. Weight, maintenance, and other so many other impacts. Yeah. So coming to that is what now what you are asking, I just kept it here. So there is always a need. Now I have designed a material which is working in some band of frequency. Let us say for example 4 to 18 gigahertz. I gave something, you will say no, I want now from 2 to 18 gigahertz. Now if I design with the 4 mm thickness, you will say 4 is enough, now I want in 3 mm. So the things, so बोलते हैं ना पेट कभी नहीं भरता वाला केस है. So you will be asking more and more. So now these are the problems which I want, if some students are really interested, will be happy to work with them. So now there is a work, so people are working with the magnetic material, dielectric material. Now people are doing with the combining both the material along with the metamaterial, and we have always requirement. If someone can come up with a better solutions what we have today, we will be happy to look into that in terms of the weight penalty, in terms of the performance, in terms of the thickness. If it is working fine, we can look into the those aspect, or maybe there's some new way to designing those materials. And then is coming is the last slide of my talk is now whatever I told is only for the RF. Now I have a radar which can see a aircraft initially 200 kilometers. Now that 200 kilometers has become 100 kilometers. Now I have other sensors is sitting, which is IR sensor, infrared sensor. Now if my range of the RF sensor has come down so much that my aircraft is reaching up to that level, now the IR is also picking up. So it is becoming not only the RF, it's RF plus IR optimization. So now we are into that stage of the problem where we are looking for a multispectral problem. So if someone can give me a material system which is working into the RF also and to the infrared also, 8 to 12 microns, 3 to 5 microns, we have a lot of requirements from that aspect. And then I have not kept one more slide was there, where we are now looking also the RF, IR and the visual also. So it's a combining, so multispectral is coming, so it's more and more complications, so we are adding on to the problem. 4. Yes, 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 yeah. So this is the another area where multispectral signature reduction is the one of the area where a lot of activities need to be done. So with that I will stop. I will just wanted to thank my director and the team member of the ADE for giving me this opportunity to speak to the in this forum. With this I will stop. Thank you. Anyone, anything, any curiosity to understand or wanted to free feel to ask? Yeah, please. Mike.
See, I'm from Air Force, so this question is pertaining to lab to field. So, where do you think your product or research reached where we are actually putting it into, like we are already doing LCA Mark 1, Mark 2A. So, is it going to see in sometime in future, maybe near future, that this material is used in our these designs? Because you are all from ADE, so you can tell me better than anybody else.
So already, I mean, we are designing for the next generation, as you are aware of, uh, which is already in the open forum now. The AMCA is already there, is sanctioned project. But the technology which you are developing for the upcoming aircraft, which is already getting infused into the what you just said the programs. I will not go into the more details, but those things are already into the Mark 1A, Mark 2 is getting into that already. So it is already integrated and flown in some of the prototypes also.
Okay. So, in this project where it is infused, so what is the factor of reduction of RCS? Um,
That I
could
will not be able to speak in the open forum, but that I just mentioned in the beginning also. Uh, any technologies which you are developing for a fifth generation aircraft, because the fifth generation aircraft ab initio is designed for the stealth. If you want to infuse those technology into any of the 4 or 4.5 generation aircraft, on the frontal sectors we can get the benefit, not all across.
okay, thank you.
Yeah. Yes, yes, yes. So it is keep on evolving things. So yes, yes. Oh no, in that aspect, no, I will not agree with that, because there is nowadays a lot of maybe in the recent wars which is happening at multi places across the globes. Uh, a cheaper version of this with a stainless solution is working very good. So you have a small bird, low cost bird. It's sometimes called people called as a kamikaze drones kind of thing. So it will not a drone basically. It may be this bird, maybe a scale down, very low signatures. One time go, finish the job. That's it. It will not be recoverable. Yes. Now EW is coming in a big way. So even though you have technology, they are getting jammed and many things are happening. Yeah.
Uh, but if we have a carbon nanotube structure, so you said metal behind it. So instead of having metal right behind it, if we put a layer of, it's extremely light and this thing, carbon nanotubes, a mesh,
Yeah.
then the property of the carbon nanotubes would be to get the radio energy, radar energy, and dissipate in the lattice of these fiber. Is that something?
Yeah, in this domain actually a lot of activities has been done. So CNTs and even graphene and other materials, carbon based these particles have been used as an absorber. So what they do basically, they will mix it in the resin systems while curing the things, and it will become a part of the airframe itself. So CNTs have been used, but only my personal the observation is that these are all anisotropy material. So getting a repeatability is the question mark on a larger scale. So that is what otherwise more or less it works. So we have some of the solutions CNT based also. Yeah, yeah. But again now again we have to see the performance also. So there are multiple parameters. Yeah. Yes.
Sir, recently, what you see in the air defense system, because what you learn from till now. So when a target is there, that means army, that means some target comes and it is detected by the radar, and then again it is intercepted. So for the interception, you are sending the missiles and all the things, and a lot of money has been spent for that one, for the sending that one. And recently some technology what you got from the newspaper, like Israel, they're using the laser technology to directly hit to this aircraft. So what is India's stand using the laser and sending the energy to destroy that one instead of missiles?
Okay, I will not go into too many details on the programs of the country. Okay, but just in a general way, I can say I was just telling in the beginning also. Radar can see very far. We are talking in 200, 300, 400 kilometers compared to any other sensors. So, or let me tell you in other way also. Now we are talking about the ground-based radar. It has a huge volume. It can search in a large space. Okay, even though my aircraft which is designed on the X band, which is a very low signature, not in the L band or the UHF band. UHF band can still search and tell me that in this area there is a one aircraft which has come. Now any interceptor has gone. Now the interceptor for him, that particular aircraft which is working in X band, now my signature in the X band is so low, for him to catch me will become a problem. So, but I will not go into the other part what you are asking. I am just giving one example. So, you have to reach to first to that level where you are, that is what I said. Now, in this particular example, what we are saying, now my RF has reached to the range of the IR. So, now RF and IR has become critical. So, what you are saying tomorrow, if further it will go down, then other parts will also will become critical.
Sir, good evening, sir. Sir, here, sir.
Please.
Sir, some radars are able to detect the which are using the very high frequency or ultra high frequency. They are able to detect the stealth cam, means aircraft.
That is what I was just explaining. You can see your lower band frequency radars will be able to see. It will tell in that volume there is a bird. But where is that bird? For that to, I mean, see, there is a radar which has seen 500 kilometer away, there is some signal has come. Now they will intercept some fighters or they will launch some missiles. They have a range of, for example, assume that I am carrying an aircraft, I am carrying a weapon which is beyond visual range of maybe 100, 150 kilometers. By the time I am reaching there, I have a bird, stealth bird, whose signature in that particular frequency, which aircraft is carrying that radar, X band, where signature is so low, for that aircraft to pick me, it's too difficult. Even though they knows that someone is there in that space.
So there's the Russian detector which has just means during that Sindur also, Sindur operation, they are able to detect some stealth
See, no, no one is flying the stealth bird in this zone.
Okay, means
It's all under development.
sir, Indian defense also means has taken some steps to detect this type of things. Or
No, India, there is one program which is there in the internet. You can read it about the AMCA, Advanced Medium Combat Aircraft. This is the India's first 5th generation stealth fighter, which is under development. So we have other platforms. Those are all 4.5 generation aircraft. It is not designed for the stealth.
okay, thank you, sir.
Thank you, sir. Thank you, Dr. Vijay Kumar Sutrakar, sir. Your impactful presentation absolutely created the difference. I believe our young talented students have already inspired with all these things for the betterment of the nation. They will be coming forward. I request our Honorable Vice Chancellor, Professor Priyadarshan Patra, to felicitate Dr. Vijay Kumar Sutrakar, sir. Welcome one and all to the valedictory hours of ICATS 26, where mind unite